Hello, and welcome to this tutorial on the Munkres assignment algorithm, also known more commonly as the Hungarian algorithm. In this video, we will cover the definition of an assignment problem, an explanation on how the Munkres algorithm solves this problem, a full step-by-step example of the algorithm in action, and finally, how this algorithm is implemented in code and the time complexity of it. So, what is an assignment problem? Well, the formal definition is as follows. The problem instance has a number of agents and a number of tasks. Any agent can be assigned to perform any task, incurring some cost that may vary depending on the agent-task assignment. It is required to perform all tasks by assigning exactly one agent to each task and exactly one task to each agent, in such a way that the total cost of this assignment is minimized. Now, this just sounds like a bunch of nonsense, and I don't expect you to understand it just from this definition, so let's have a look at an example instead. Here, we have a list of workers, or agents, and a list of tasks. This table contains values that represent the time it would take for that worker to complete that task. Seeing as all these tasks need to be done, and each worker can only do one task, what is the best way to assign these tasks to produce the smallest total time? We could of course try to pick options that look like the best, picking the smallest values in the grids, 5 for worker C, 8 for worker D, and 37 for worker B. This however leads us to take a really large value for worker A, 92, giving us a total of 142. If we change this by taking the smallest value for A, we then pick the remaining values as small as possible to get a smaller total of 140. Well, this is definitely better than 142. How do we find the best option? To do this, we'd have to try every possible combination. With 4 workers and 4 tasks, this leads to 24 different combinations. While this may not be too many, if the number of workers gets very large, we end up with n factorial combinations, where n is the number of workers. This makes it impossible for very large values to be run in polynomial time. To do this, we will instead use the Munkres algorithm. The Munkres algorithm will solve this problem in polynomial time. Given that we have an equal number of agents and tasks, we can follow these steps to solve the problem. Instead of going through these steps right now, I'm going to show you them to you using an example we just looked at. Here, we have the table we looked at earlier. Fortunately, it's an even 4x4 matrix, so we can apply these steps directly. Don't worry though, if you're wondering what happens when our matrix isn't even, we'll get to that later. Just hold on a bit. So, step 1. We need to find the minimum value in each row, and subtract it from every value in that row. Looking at this example, the minimum value for worker A is 69 in task Z, for worker B it's 37 in task Y, worker C is 5 in task Z, and worker D is 8 in task X. Now that we've identified these minimums, we have to subtract them from every other value in that row. This will leave us with this reduced matrix. Having done this, step 2 is to repeat this on all of the columns. For the first 3 columns, the minimum value is 0, and so we don't have to subtract anything. For task I, this minimum value is 15. So we'll subtract this from all other values in that column. This leaves us with a matrix with multiple zeros in it. These zeros are all potential solution matches for the algorithm. To check to see if we have enough good pairings to create a solution, we move on to step 3. Cover all of the zeros with as few lines as possible. This step can be quite tricky, but a good tip is to start by drawing the lines to cover as many zeros as possible, and then moving down to lines with less zeros. In this instance, it took a minimum of 3 lines to cover all the zeros. Seeing as n is equal to 4, we are currently not finished. The next step is to find the smallest uncovered element. In this example, it is 6. We take this value and subtract it from all other uncovered values. We also have to add this value to any value that's covered by 2 lines. Having done this reduction, we then repeat step 3, redrawing the lines to cover zeros with the minimum number of lines possible. In this case, we end up with the minimum number of lines being 4, the same as n, meaning that the algorithm is finally finished. The last step is to select the zeros in the table so that each row and column only have 1 zero selected. To make sure you get the correct pairing, start by circling the zeros in the rows that only have 1, and keep going until you have n zeros selected. In this case, the final solution actually ends up as the second try we did, with the pairings AZ, BY, CX, DI, creating the total 140. Now that we solved the most simple case, we need to consider the other cases in which you can use this algorithm. These cases are if the matrix is uneven, or if you want to maximize the solution rather than minimize it. To solve this problem for a non-square matrix, we must simply turn it into one by adding dummy columns or rows. The values of these dummies equal to the largest value in the matrix, because we want these options to be the least preferable option. They represent not using that agent or task at all in the solution. Let's pretend the previous example only had 3 tasks and 4 workers. We cannot directly apply the Munkres algorithm because the matrix is not square. We need to add a dummy task. The largest value in the matrix is 98. So we set all of the values in the dummy column equal to 98. Now that we have a square matrix full of values, we can solve the problem normally. Remember though, any result from the dummy column is excluded from the final solution, so whichever worker ends up with 0 in the dummy column doesn't add the value of that solution to the final result. Now let's look at a maximising problem. Like non-square matrices, we take an initial step to convert it to a normal minimising problem and solve normally from there. For this initial conversion step, we take the maximum value in every row and then subtract all other values in that row from that maximum. This may sound confusing, so let's have a look at our table again. So now the values of these tasks represent profits rather than cost, and so we want to earn as much money as possible. We start by finding the maximum value in each row. Taking this maximum, we then subtract the values in the rows from this maximum, giving us these results. Why did we do this? Well, now that we have done this, all of the small values in the matrix have become very large, and the large ones very small. The maximum values now equal 0, which means they are possible pairings, and seeing as we want to find the maximum solution, this sounds pretty good. From here we can solve this problem exactly the same as a minimization problem. Just remember to find the original matrix, not the minimized one at the end, to find the actual values for the maximum solution. There is one final note if you want to combine these two processes. When maximizing with dummy columns, it works exactly the same except for the fact you need to set the initial values of the dummies to 0 rather than the maximum. This is so that once you complete the conversion step, the zeros will become the maximum value in that row, making it the same as the minimizing problem. Let's wrap up everything we've learnt so far in one big example. This example question is taken from OCR D2 exam paper on May 2011, question 2. If after this video you would like some more examples to work through, I'd recommend checking out some of the other D2 papers on the OCR website for more Munkres algorithm problems. In this example, Granny is on holiday in Amsterdam and has bought some postcards. She wants to send one card to each member of her family. She's given each card a score to show how suitable it is for each family member. The higher the score, the more suitable this card is. Here is the table of family members and postcards. As you can see, there are 8 postcards and only 6 family members. This problem is also a maximising problem because the higher values represent a higher level of suitability of the postcard. The first step is to add our dummy columns to the table. These dummies will represent postcards that aren't sent to anyone. We set these values to zeros because we are maximising in this example. We now need to do the conversion step from our maximising problem to a minimising one we can solve. Start by identifying the maximum values in the rows. We then subtract all of these values from these maximums, giving us now a minimising problem. Now if you remember our steps in the original algorithm, step 2 is to find the minimum in each column and subtract it from all other values in that column. Note that in this example, only the dummy columns end up having no zeros in it, so these are the only 2 that need to be calculated. Now that we have reduced our matrix, we move on to step 3. Here, we draw lines so that we cover as many zeros as possible, in order to cover them all with the minimum number of lines. In this case, it takes 5 lines to cover them all. Seeing as 5 is less than 8, our n, we need to further reduce this matrix. The first part of step 4 is to find the minimum uncovered element. In this case, it is 1, marked on the slides for convenience. If you can remember back to this step in the first example, we do 2 things with this minimum element. First, we identify all values that are covered by 2 lines, and add this minimum element to it. We then subtract it from all other uncovered elements in the matrix. Now that we have done this, we go back to step 3 and draw our lines again. This time I've drawn all the lines that cover multiple zeros, but as you can see there are still 3 more zeros that are uncovered. Because no more than one of these 3 can be covered by a single line, we have to draw a line for each of them. This gives us 8 lines that cover all the zeros, and this is the minimum number required. From here it is simple to find the solution. Although many of the rows and columns may have multiple zeros, we can only have 1 in each row and column. Start by selecting the zeros in the rows and columns that only have 1, and then move on to the rest. Once you get the hang of it, you can complete this step very quickly. Now that we have selected the zeros, we can look back at the original table and add up the results. As you can see from here, Adam gets postcard V, Barbara gets postcard S, Charlie gets postcard U, Donna gets postcard P, Edward gets postcard W, Fiona R, and Q and T are not sent to anyone. This creates a total suitability rating of 36. Now let's look at the runtime of the algorithm. As I mentioned earlier, this algorithm runs in polynomial time, but let's have a more in-depth look. This is an example of the pseudocode for this algorithm. This video isn't on how to program this, so I won't go into too much detail, but there are a few key things to note here. Time complexity is usually controlled by how much a program loops. If we think about the process we did, at every step we have to look through both the rows and the columns. Therefore, every time we reduce the matrix, we go through n by n elements, so n squared elements. The maximum possible number of times we would reduce this matrix is by n, seeing as if you reduce a row n times, every value would be 0. This makes the end result equal to big O of n cubed, as we will go through n squared n times. That concludes this tutorial on the Munkres algorithm. I hope you have a better understanding of the algorithm than before you watched it. I'd recommend working through a few examples of your own so you get the hang of doing these problems for yourself. Thank you for watching, and good luck in your studies.